Here in video 20A, we talk about the properties of linear materials and how these arise from the molecular structure. First, we'll define some terms. We talk about the proportional limit, meaning the point above which Hooke's law no longer applies. So in this diagram here, the proportional limit is this linear region. And we refer to the stress and the strain as sigma PL and epsilon PL as the stress and strain at the proportional limit, where this linear regime no longer applies. Above this area, the materials are nonlinear. We refer to the tangent Young's modulus as the derivative of stress with respect to strain, that is, the slope of the curve on a stress-strain plot. Below the proportional limit, the tangent Young's modulus is simply equal to the Young's modulus. That if the tangent Young's modulus decreases with strain, that is, if the second derivative of strain with respect to stress is negative, we refer to that as yielding behavior. If instead the tangent Young's modulus increases with strain, that is, the second derivative or the curvature is positive, we call that strain hardening. Whereas one that maintains an equal Young's modulus, tangent Young's modulus over time is linear. We refer to elastic deformation as deformation that's reversible. This occurs because molecular bonds stretch but don't break. Whereas plastic deformation is irreversible because the molecular bonds break. And because of this, we could use the word either elastic limit or plastic limit, which we might call sigma sub E for elastic, or epsilon sub E, as the point at which the bonds switch, where it switches from linear, that is elastic, to plastic, and that is the point at which the bonds stretch so far that they break. So in this figure, here we're within the proportional limit, and at that point, if we were to let the strain off, we would be going up like this, and if we then reverse or remove the strain, the stress, we would go right back on the same line, and that's completely elastic recovery, and there's no residual strain. If instead we keep pulling past that elastic limit, and then at some other point take the strain off, we will have elastic recovery still, but we will leave this region of residual strain, which is deformation that remains when the stress is removed due to plastic deformation. So a linear elastic material is one where the elastic limit is approximately equal to the proportional limit. That is, where all the elastic deformation is linear, which is what we see here. We're below this elastic limit, it's basically straight. A ductile material is one where new molecular bonds can form during deformation. So this allows plastic deformation. That is, the material has not broken, it is simply deforming, but it's deforming irreversibly because the bonds have formed in these new places. And finally, brittle materials are ones where the bonds, once the bonds break, they do not reform, and so there's no plastic deformation. So as we see here, a brittle material will have linear elasticity up to the point where it fractures or breaks with no plastic deformation. These materials' properties are measured by stretching material or compressing material. I'll show here the example if a material is exposed to uniaxial stress, often with a rod-like or wire shape. So if one pulls out some distance and then returns. So pulls, returns, goes farther, returns, farther, returns, farther, returns, and at some point when we return, it goes back and you see that there's some strain. So when that residual strain is greater than 0.2%, which is often a good point as just being measurable, the point where the residual strain is greater than that, when that's then referred to as exceeding the elastic limit, and so that's how this is found. We'll now look in more details at the properties of ductile linear materials. The yield point, which is characterized by the yield stress and the yield strain, is the point at which the material yields. That is, where it goes from a constant Young's modulus and tangent Young's modulus to a decreasing tangent Young's modulus. Now, for most ductile materials, this is equal to the elastic limit. That is, it only maintains reversible deformation within the linear range. Now, at some point, as the material yields, it reaches a maximum stress that's the highest stress the material can withstand prior to failure. This may not be the stress at failure because the stress often drops as you start approaching failure. This happens, if for no other reason, because the material, as it stretches in the direction it's being pulled, gets narrower in the cross-sectional geometry. And as the cross-sectional geometry shrinks, even if the stress were to remain the same, the decreasing geometry causes a decreasing stress. When we measure the maximum stress during tension, refer to that as the tensile strength or ultimate tensile stress, whereas the maximum stress measured during compression is referred to as the compressive strength or ultimate compressive stress. Now, another concept is the breaking strain, which is the maximum strain that occurs at failure. Now, this is in contrast with the maximum reversible strain, which is the strain right at the elastic limit. Note that for ductile materials, the reversible strain is much less than the breaking strain because of this long yielding period here. Whereas in contrast, the maximum stress is fairly similar to the elastic or yield stress that is at the end of the proportional limit. We next look at properties of brittle linear materials. So these materials undergo no nonlinear or plastic deformation, and so there is no elastic limit, there's no yield point, and no reversible strain. Instead, we simply have the maximum stress at fracture and the breaking strain at fracture. And for brittle materials, all the deformation prior to fracture is linear. Because of this, the maximum reversible strain and the breaking strain are identical. Both ductile and brittle materials are types of rigid materials. What that means is that they exhibit only small elastic deformations. That is, that reversible strain is always much less than 1. For brittle materials, we saw that the ultimate tensile stress, or the maximum stress, is the Young's modulus times the reversible strain, because that all occurred within the linear range. Now, within the ductile materials, the ultimate tensile stress, which is still the stress at the elastic limit, this is approximately equal to the Young's modulus times the reversible strain, because it's completely linear within this region. So we see that for both types of these materials, if we divide the ultimate tensile stress by the Young's modulus, we get approximately the reversible strain, which, as we noted above, was much less than 1. So this is why, even if they can undergo large plastic deformations, that is, even ductile materials, still have this relationship of the ultimate tensile stress divided by the Young's modulus being much less than 1, a fact we used when we talked about deformations of pressure vessels. So those things are about rigid materials. That is, rigid materials have deformations within the elastic limit of much less than 1. However, elastomeric materials can exhibit large deformations within the elastic limit. Because linearity is never maintained for large deformations, all elastic materials are nonlinear, and these are addressed in the next 2 lectures.